Hello oceanography students. In this lecture we're going to talk about coastal environments and in some coastal environments we also have estuaries, so we'll talk about estuaries as well. So what is the coast? The coast consists of all of the terrestrial areas that border the ocean or a sea or an estuary or a wetland. So it's basically all of the area that is affected by the ocean. And you can find ocean-related features there as well. So, for example, here is a cliff-lined coast, and you can see a number of features here. We have the shore, which extends up to this cliff line, out to the low tide shoreline. The whole shore environment, which includes the shore and the near shore, extends all the way back to this cliff and out to beyond where the waves are breaking. Okay, and then beyond where the waves are breaking, we call that the offshore environment. Now the coast is going to be everything that is above water that extends to as far as it's affected by ocean conditions. Okay, so what kind of processes affect what the coastline looks like? There are three main categories: waves, sea level, and processes from land. So with wave activity, we have either erosion, which means that it's taking sediment away from the coast, or deposition, which means it's bringing sediment towards the coast. Okay, and we've kind of already gone over this, but waves carry sediment and other material to the beach or the berm, and also away from the beach, right? So when a wave comes in, we call that the swash, and the remaining water that goes back out is called the backwash, right? So remember, we talked about how in the summertime, when there is lower wave activity, the waves are dominated by the swash, which carries sediment back onto the beach. And in the wintertime, when you have very heavy wave activity, that's dominated by backwash, because when the waves come in, some of the water seeps into the sediment, but because so much wave activity is occurring, the sediment cannot dry out between waves, and therefore once the sediment is saturated, it can't take in any more water. So instead of having some of the water seep into the sediment, all of the backwash comes back out, and with it brings all of the fine particles, and those fine particles can be deposited out on a sandbar. And so what that ends up looking like is, when you have light wave activity, you have lots of fine sediment on the beach, and when you have heavy wave activity, that fine sediment gets taken off of the beach, and what remains are the larger rocks. Okay, wave activity also causes something called longshore drift. So on steep shores, the sediment will drain just straight back into deeper water, right? So the waves come in and the waves go back out, and the sediment just drains away from the shoreline, like when we had with the heavier wave activity, right? Or this also happens when you have a steep shoreline, a steep beach. But on flatter shorelines, the sediment is actually moved along the shoreline. So it doesn't just go straight back out. It actually gets pushed down the beach or down the coastline. So the net movement of sediment along the coast from the up coast, which is where the waves are coming from, to the down coast, which is the direction where the waves are going to, is called longshore drift. And this is both driven by wave activity and by current activity. Okay, so let's look at how it's driven by wave activity. So first, you have a wave that approaches the shore at an angle, right? Lots of times the waves do not come just parallel into the shoreline. They actually come from the north or from the south, right? So in this example, we have waves that are coming from this direction, right? Refraction will occur and the wave will bend. The water will rush up, which is shown by these darker arrows here. The water rushes up onto the beach and then returns back down away from the beach, right? Which is shown by these little arrows, right? So the waves refract and they bend so that they are nearly parallel to the shoreline, but they're not perfectly parallel, right? So you notice that this arrow is not perfectly straight. It would be like this if it was straight, and then the sediment would go back out. But instead, it's coming from this angle, and so it's pushing water up here, and then the sediment is coming right straight back down because that's based on gravity, right? And so what you end up having is this kind of zigzag motion where the sediment ends up getting pushed down the beach. So here's the sediment came from here and now it's down here. Then you have another wave coming in and it's bringing that sediment back up, but it's coming back down here and so on and so forth, so that we end up having a pile of sediment down the coast. Okay, so water rushes up the beach at an angle but returns straight downhill. The sediment grains travel with the water zigzagging down the beach away from the direction of approaching waves. It's also current driven because the wave activity actually creates a current. So you can see longshore current shown here. And so just the general movement is going to be down the coast. And so that also contributes to, once the sediment comes back into the water, if it's being brought in and making the water turbid, that turbidity is going to be brought down the beach to be deposited elsewhere. Okay, and so this is a picture of that. This beach experiences longshore drift, where the waves are often coming from this angle, and therefore you can see that the sediment is getting deposited down the shoreline. So they've put in these groins to try to keep it so that the beach doesn't get completely washed away and piled up over here, so that you can continue to have beach. As you can actually see as you go down the beach, you can see that angle there. Okay. Wave energy also affects the shoreline, as we've talked about before, because the waves will refract and bend towards the shallower areas. So when you have land that juts out, that wave activity is going to be brought to there, and then the drift is going to take all of the fine eroded particles and deposit them onto the inland, the little cove areas on the beach. And so in this way, you end up having rocky shorelines where the land is jutting out, and more of a berm or a beach with fine particles where the land is jutting in. Okay, and so we can see that here where land is jutting out, we can see the wave activity is very strong. This also is created by wave activity. Also, obviously, there was rising and falling of sea level as well, which contributed to this carving out of this canyon. And of course, the smokestacks that we see, these large piles of rocks, that's also because of the wave activity, right? So this rock was probably part of this cliffside, and it eroded away over time. Okay, so wave activity affects the coast. Sea level also affects the coast, right? Which I was kind of hinting at with that little area where the canyon had been created there. So there's two different types of sea level. There's eustatic sea level change, which means that the sea level changes all over the globe, whereas there's also local sea level change, which means that the sea level is only changing in one specific area. Okay, so sea level can change because the level of the land changes, the level of the sea changes, or both of them change. So we have eustatic sea level changes, which means that you can see a sea level rise or a sea level fall that is measurable all over the world. Okay, this can be attributed to the amount of liquid water on Earth changing. For example, if you have glaciers melting, then that means that the amount of liquid water is increasing, and you would expect sea level to rise globally. Or if you have a glaciation event or an ice age where you have liquid water that is being frozen, then that's taking the liquid water out of the oceans and making the sea level go down all over the world. We can also have the area of the ocean changing. So if we have the ocean getting larger, right? So that means like you have a bowl of water, right? You can either fill the bowl of water up with more water, right? That would mean amount of liquid water increasing. Or you can have a different size bowl with the same amount of water, right? So if your bowl is bigger, then the water level is lower. If your bowl is smaller, then the water level is higher. That's what that means. Another factor that can affect the sea level on a global level is the temperature of the water, because warmer water expands, and therefore when the water is warmer, you would expect the sea level to rise globally. and colder water contracts. Therefore, if the water is globally colder on average, then you would expect the sea level to go down. We also see local sea level changes, and these occur due to tectonic movements that can cause uplift, meaning that the land is actually rising up. Therefore, the where the water line is hitting is lower, or subsidence, which means that the land is actually sinking or falling down, which means that the sea level would actually rise in that local area. Waves and currents and storms and other water movement can also affect the sea level there, right? So if you have strong wave activity, then that actually increases the sea level. And in hurricanes, when you have a storm surge, that also increases the sea level. Okay, so this image here is showing an example of eustatic sea level change, although it's only showing it in one small region. So here we have Florida, right? And you can see Miami. So this was about 18,000 years ago. The green represents land that is out of water, right? So you can see that 18,000 years ago, Florida would have been much larger, right? This is future, which I can't remember what the future date is, showing sea level rise, and therefore Florida is much smaller. Most of it is actually, probably a third of it is actually underwater now, okay? And those changes are due to the overall amount of water that's on land. Right here, there was an ice age, and therefore the amount of liquid water in the oceans decreased, and therefore sea level went down. Here we have global warming causing our glaciers to melt and putting liquid water back in, and therefore liquid water rises up, and you have the sea level rising. Okay. Sea level can change because the level of land changes, the level of sea changes, or both. So we have eustatic sea level, which we just talked about. We have local sea level changes as well, which we also just talked about. So in this video here, this is showing us what can happen on a local scale based on the weather. See if it plays for us. Okay, so we can see here this dotted line is the high tide level. This is the low tide level, right? So the water level right now is in between high and low tide. And now we have a winter storm or a late summer hurricane, okay? So now the water level rises up, and you see that it's causing erosion of the land up here. That eroded material gets deposited down farther. So the actual shape of the shoreline is changing. And eventually, what happens, well, these people who put their house right there on that cliffside that had this beautiful view no longer have a house. So you have to think about those kinds of things when you are buying homes and building your homes. So normal weather, they were fine. But when you had this strong storm, sea level rose up and we had major erosion that occurred. And you can see this dotted line is showing you where the land used to be, and you can see where the land is now. So it completely changed the actual shape of the shoreline there. Okay, processes from land also affect the sea. Okay, things like streams or rivers. When you have increased flow of river activity, that causes erosion around the land as well, and so that can actually cause a change in the actual shape of the shoreline due to increased river activity, or you can have decreased river activity, and that will also change the shoreline. When the land freezes or thaws, it also has a way of basically contracting or expanding, and so that's going to change the shape of your shoreline. Plant roots are also very important because they decrease the amount of erosion that occurs. So if you had an event where your plants were pulled out and you didn't have those plant roots anymore, you could have major erosion that occurs due to just general normal wave patterns and water movement patterns. And so a lot of places see that it's very important to have plants around the shoreline, natural plants around the shorelines to keep from erosion from occurring. And then glacial activity will also contribute to this, right? If you have glaciers, that means that you have very heavy ice on the land, and that will actually cause the land to subside or go down, which means that the sea level would actually be higher in comparison. Then when you have glaciers that melt, that land can rise back up, and now you have sea level declining, and that would be on the actual rising and falling of the land due to that glaciation would be on a regional scale. But if you have a global event where the glaciers are melting or the glaciers are freezing, then obviously that also would happen on a large scale. Okay, and then rivers can also bring with it lots of sediment. So if the sediment accumulates in different areas, then we have new land that gets created and your shoreline changes too. Okay, so processes from the ocean affect the shape of the shoreline. Processes from land also affect the shape of the shoreline and where the water level is hitting. So what we end up with are coasts that are either termed erosional coasts or coasts that are termed depositional coasts. So erosional coasts mean that you have erosion dominating the environment, and so in that scenario, you would have lots of cliffs, and lots of times those erosional shores are have a lot of tectonic activity around them, right? We have fault lines or convergent zones just off the shore. That's actually causing the rise of the land or the subsidence of the land. Depositional shores are shorelines where they are dominated by deposit of sediments, and therefore they're going to have nice wide beaches or berms, and they also are characterized by having barrier islands. Lots of times depositional shores are actually lowering, the land is actually lowering, and therefore sea level may be rising in those locations. So here's an example of an erosional shoreline. We can see the cliffs, and you have headlands with these coves or inland kind of sheltered areas, right? We talked about wave activity hits the headlands and is reduced around here. And so over time, that wave activity actually causes what are called sea arches or sea caves, and can also eventually cause erosion of the land that's jutting out, and you can have sea stacks that get created. So we can see that in this image here. Right here is a series of what happens when you have wave activity that's being directed at the headland. So one large crack opened up by water activity. The crack grows into a cave. The cave becomes larger. Eventually, the cave breaks through the headland, and you have what's called an arch that forms. And then eventually, with increased activity, that land up here collapses down, and so this whole land now is its own little rock, which we call a smokestack, or a rock stack. And then over time, that gets eroded as well until it's smaller rocks. Okay, we see this a lot on our shoreline. Depositional shores are more of what you see oftentimes along the east coast of the United States. So with depositional shores, we have wave activity that causes longshore drift, and so you have sediment that gets carried down the shoreline, and that sediment eventually piles up and causes barrier islands, which then create little lagoons, which are small estuaries that are separated from the land. So this shows you how that happens, right? Wave activity is coming from this direction, therefore longshore drift is going in this direction. So it's taking sediment from over here and depositing it down the shoreline. That gets deposited to the point where you can actually have a island that forms here, and that essentially is a barrier from this water right here, and a barrier from wave activity getting over here. So we would call this basically a lagoon. Okay, so just to recap, what can affect the coastline? You should say that the coastline can be affected by wave activity, both from waves coming in and depositing sediment onto the beach or taking sediment off of the beach, and also waves that cause longshore drift and deposit sediment down the shoreline. You should also say that the amount of water in the ocean can change, or the amount of the sizes of the ocean can change, and that would cause eustatic sea level rise or fall. And you should also say that we can have changes in a regional scale that are based on tectonic activity, based on glaciation, based on rivers, all kinds of stuff. Okay, So what is eustatic sea level change? You should say that it is sea level change that could be measured all over the world. How can eustatic sea level change occur? I just kind of went over this, right? So it can occur by having the amount of liquid water in the oceans change. If the liquid water increases, your sea level increases. If liquid water decreases, your sea level decreases. You can have a change in the size of the ocean, the actual geological part of the ocean. And so if your ocean is bigger, then sea level goes down. Your ocean is smaller, then sea level goes up. And then finally, you can have a change in the temperature of the overall ocean. Temperature warming causes expansion, and that would cause sea level to go up. Temperature cooling will cause contraction, and that would cause the sea level to go down. What about local sea level? How can that change? So you should have said that local sea level can change due to tectonic activity, which might cause uplift of the land, which would cause sea level to go down, or it can cause subsidence of the land, which would cause the sea level to rise up. And it can also be caused by storms and wave activity as well. Okay, so finally, along many coasts you have what are called estuaries. Estuaries are a partially enclosed body of water in which you have fresh water entering on one end, on the land end, and you have salt water entering on the ocean end. Okay, so essentially this is an area that is semi-enclosed by land, and it is an area where fresh water is meeting the ocean. Okay, and so therefore it often exists around river mouths. So here's our estuary, the San Francisco Bay Estuary, which will be the topic of our next video for this week. There are 4 different types of estuaries based on how they were created. So we have a coastal plain estuary, which occurs when you have a river valley that is drowned out due to sea level rise, right? So you have, this would be a narrow river coming out, but the sea level is increasing, and therefore it's drowning out that valley. So that's a coastal plain estuary. A fjord is glacially carved. So you have a glacier here, and that glacier carves out the land as the ice is forming. It actually breaks rocks off and can carve out the land in that way. And so a fjord is due to glacial activity where the glacier eventually melts and you have ocean water coming in and flooding it. A bar-built estuary, which is also called a lagoon, occurs when you have longshore drift depositing sediment and creating sandbars or islands or barrier islands, and that creates what's called a bar-built estuary or a lagoon. And then you have tectonic estuaries, which occur because the faults are actually, the tectonic activity is actually lowering the land level, and when that land level lowers, the rivers that are coming from that area actually flood the valleys, and also the sea level is coming in and flooding the valley as well. Okay, some examples of this. The Chesapeake Bay on the east coast of the United States is an example of a coastal plain estuary. The Glacier Bay in Alaska is an example of a fjord. Matagorda Bay in Texas is an example of a bar-built estuary, and then San Francisco Bay here is an example of a tectonic estuary. Okay, now the way that the water circulates in estuaries depends on basically how strong the river input is and also on how deep the estuary is. So we have 4 main categories based on the way that the fresh water is mixing with the salt water. So we have a vertically mixed estuary, which happens in shallow estuaries. We have a slightly stratified estuary, which happens in fairly deep estuaries. Highly stratified estuaries are very deep, so think fjord. And salt wedge estuaries occur when you have a very strong flowing river coming out. Okay, so let's look at these examples. Here we have a vertically mixed estuary. Vertically mixed, that means that when you go from the surface of the estuary down, the salinity level is the same. Okay, so what you would expect is here's the head of the river. Okay, so that's fresh water coming in. Here's the mouth of coming from the ocean. So you would have salt water coming this way. So as you go from the salt water towards the fresh water, you will see that the salinity is decreasing, right? Here's the salinity, 30, 20, 10 parts per thousand. All right. Vertically mixed again means that when you go from the surface down, it's the same salinity all the way to the bottom, right? So right here at this location, salinity is 10 parts per thousand. Right here, salinity is 20 all the way down. Here, salinity is 30 all the way down. Okay, so it is vertically mixed. In your book, it says well mixed. Slightly stratified means that as you go from the surface down, the salinity is actually changing slightly. Okay, your book also calls this partially mixed. So in this example here, we would have a salinity of 10 parts per thousand, but then as we go down, we would probably get into a salinity of about 12 to 15 parts per thousand, gradually increasing as you go down. Because generally speaking, if it's deep enough, the fresh water is going to come out and it's going to end up floating on top of the salt water that ends up coming in at the bottom. Therefore, the salt water, it's going to be saltier. It's going to be saltier on the bottom than it is on the top, but only slightly because it's not really deep enough to see it to the full extent. But this next one with a highly stratified estuary, you can really see a change in the salinity from the surface down. So again, here's the river. Fresh water coming in, okay, salt water is over here coming in. Now because the water is so deep, the fresh water actually comes out at the surface and the salt water goes in deep down. So as you go from the surface, so you have, so these blue lines right here are showing you the salinity all along there. So this is all salinity 10, this is all salinity 20, this is all salinity 30. Okay, so we go from right here, which is 10 parts per thousand, and then you go down and you get to 20 parts per thousand, then you get to 30 parts per thousand. Okay, so that is highly stratified, meaning that there are specific layers of salinity or also of density. And this would occur in a fjord, and so your book actually calls it a fjord estuary. And then finally, the last kind is a salt wedge estuary. Salt wedge estuaries occur where you have very strong river input, meaning that the river flow is very high and fast. So in this case, what happens is the river actually empties out and the whole surface of the estuary ends up being fresh water or close to fresh water, and the salt water from the ocean is actually only coming in at the bottom. So it creates this kind of wedge, which is they call a salt wedge, where you have salt water kind of at the bottom and fresh water at the top. So again, here's salinity of 10 parts per thousand, here's salinity of 20 parts per thousand, here's a salinity of 30 parts per thousand. So it creates kind of this wedge of salt water that comes in, and at the surface you have fresh water coming out. Okay, that's it for this video. If you have any questions, please post them under the weekly discussion. If you have any urgent questions, you can always email me as well. Okay, thank you.